Dear students, already we have discussed one application of Biot-Savart's law, that is the magnetic field intensity due to state current carrying wire of infinite length. Now in this video we have to discuss the magnetic field at the axis of a current carrying circular loop. Okay, suppose it is a circular loop, current carrying loop. I current is flowing in this loop of radius A. Okay, now on its axis, that is you can see this line on its axis at the distance of x, there is a point P where we have to find the magnetic field intensity due to this current carrying loop. Okay, so to find the current carrying to find the magnetic field due to this current carrying loop, first of all we'll join these two lines, okay, and take this distance r. Okay, it is a perpendicular line here. Okay, so you can see here, to find the, you know very well, to find the magnetic field intensity, to apply the Biot-Savart's law, we have always take a small current element. Suppose del L is the small current element we are taking to find the magnetic field intensity. So we'll find the magnetic field due to this small part, and then after taking the integration, we'll find the magnetic field due to the entire loop. Okay, so at point P, okay, at point P, if we apply the Biot-Savart's law, we know the formula of Biot-Savart's law, dB is equal to mu naught upon 4 pi I del L sine theta upon r square. Okay, and since here the angle from this circular path, okay, from here to here, practically if you can do it also, you can realize also, it is always 90 degree. So it is approx 90 degree, not exactly, but it is, we consider 90 degree. So in this formula, if we take the theta is equal to 90 degree, so we'll find the mu naught upon 4 pi I del L upon r square, because theta is 90 degree, so sine 90 is equal to 1. So, and you can see the direction of the magnetic field intensity always perpendicular to the line joining. Okay, you know this is the property, and using the different rules to find the magnetic field intensity, the dB, that is the magnetic field, is always perpendicular. Just see the IBL etc., all the rules to find the direction of magnetic field. B is always perpendicular to the line joining. Okay, so it is at 90 degree magnetic field, so del B due to this del L is the magnetic field intensity. Okay, it is at 90 degree, this is the at 90 degree, so we'll take this angle phi. Okay, try to understand, dear students, this is the angle phi. Okay, and this angle, this is the 90 degree, you can see here, this is the 90 degree, so it means this small part, it is at the angle of 90 minus phi. Okay, it is the phi, this is the total 90, so this portion is the 90 minus phi, and it is again 90 degree, so this angle will be phi. Okay, simple calculation. So this angle is again phi, because this is the angle phi here. So we can resolve this small magnetic field intensity del B into its vertical and the horizontal component. Okay, horizontal component, that is the del B sine, del B cos theta, this is the angle, and the vertical, that is the del B sine phi. Clear? Now if we consider another just opposite part of this portion del L, so the same thing you will find here, and again the vertical and the horizontal component you can see here. But if you see clearly the resolution of the components, so del B cos phi of this side is equal to the del B so cos phi of this side, equal and opposite, so both will be cancelled, because this is a vector quantity and in opposite direction, so they will cancel to each other. So the components which are in this direction horizontally to this axis, all these will be added up. Okay, we can add the total effective magnetic field intensity due to this entire current carrying loop will be the integration of this del B sine phi. So here we'll write the total magnetic field B is equal to del B sine phi. Okay, put the value of the small magnetic field dB here, mu naught 4 pi I del L. I'm taking the del instead of del, I'm taking the d small, the same thing. So I dl r square sine phi. Okay, now from this diagram you can see, because this is the triangle 90 degree, this is the hypotenuse, this is the base, this is the perpendicular. So the sine theta is equal to a upon r, perpendicular to upon hypotenuse. So a upon r, just write here, sine phi is equal to a upon r. dl is here written. Okay, now it is the r cube. You can see here it is the r cube, mu naught upon 4 pi I a r upon r cube dl. Okay, now keep out the constants here, take the integration dl, and but dl that is, it is equal to the integration of the dl, it is equal to the circumference of this circular loop. Okay, so circumference, it is 2 pi a, because a is the radius of this loop, and r, from this diagram you can see r square is equal to a square plus x square using the Pythagoras theorem. Is it clear? So put here the value of the r from here and the del L. So you will write here 2 pi a here, and the r cube means a square plus x square to the power 3 by 2. Okay, so on simplification you can write like this also, because the 2 pi is cancelled by here, it is 2 times. So mu naught I upon 2 a square plus x square to the power 3 by 2. And if we consider there are number of turns n, capital N is the number of turns, so every turn will give the effect at the point P, and it will increase the magnetic field intensity. So just multiply here in this formula if n is the number of turns. So you can write in this formula mu naught n I a square, put here n only in this formula, upon 2a square plus x square to the power 3 by 2. Okay, now we can consider a special case when we try to find the magnetic field intensity at the center of this loop, at the center of the loop of radius a. Then what we'll do here, in this formula just simply write put the x is equal to 0, because you are taking x is equal to 0, you are taking the magnetic field intensity at the center. Okay, so put x is equal to 0. So in this formula if you write x is equal to 0, you will find mu naught n I a square upon 2a cube. Okay, or a cube is here the a square, so what will remain here? Only the a. Okay, only the a you will write here, to ni upon 2a. Okay, it is cancelled here, so only you can write like this. Okay, it is the 2a only. So this is the desired expression at the center, and this is due to the whole circular loop. Okay, dear students, we can find the magnetic field intensity by directly. We can find this formula by different method also. We can see here magnetic field at the center of the circular loop, carrying loop, directly we can find. Okay, so I am imaging here a circular loop, current carrying loop, and to apply the Biot-Savart's law, again we have to consider a small current element. Okay, small del L. Okay, and its radius is again a. I'm taking the a radius, and at the center its magnetic field is, we have to find. And direction, you can see what is the direction. What is the direction? By using the right hand palm rule number 1. Okay, we can find the direction of the magnetic field like this. Put the thumb in the direction of current, right hand thumb, right hand palm. Okay, and the direction, and indicate that point where you have to find the direction of magnetic field. So it is always pushing direction. So it is always upward direction. Okay, it is always upward direction. So using the Biot-Savart's law, write the formula del B is equal to mu naught upon 4 pi I del L sine theta upon a square. And here the angle is 90 degree. Okay, angle is 90 degree. angle between the del L and this line joining. Clear? So theta is 90 degrees so therefore we can write sin 90 is equal to 1. So del B is equal to mu naught upon 4 pi I del L upon A square. Okay, now keep out the constants and take the integration of this, because this is a small length. So suppose you are adding all the small length of this circumference. So take the integration, or simply you can take the sigma sign, that is the you are adding all the small parts. So del L and the total part will become equal to its circumference. So instead of this value here, we can write 2 pi A. A is the radius of this circular loop. So you can write B is equal to mu naught I upon 2A, because 2 pi is cancelled 2 times here. Okay, 1A is also cancelled. So it is the mu naught I upon 2A. And again, if the n is the number of turns, then you can write here the desired formula by multiplying this by capital N. So mu naught Ni upon 2A. Okay, so this is the desired formula. And remember, again, I to remind you, the direction of the magnetic field at the center of this current carrying loop is always directed upwards. Why? Using the right hand palm rule number 1. So thank you, students, for this topic, and in next topic we'll discuss about the Ampere circuital law.